So anyway, today what I'm going to do was go through an example that I ran last year in this class. Last year it was real time, but on using the methods that we've been talking about for fitting the early coronavirus data for spread in Delaware. So this was, I gave this lecture at the end of April last time, so we had data up till April 13th. And this is what, whoa, no. There we go. We had data up till April 13th at the time, and this was the data straight from the Delaware coronavirus website. One thing that I was interested in, because we had just covered the topics involving AIC and model selection, was basically running through these and showing how that works in this context. So, the first thing that we were looking at was basically the noise model, because we knew that we were getting noisy measurements. If you remember, a year ago, the tests were almost impossible to come by. They were not doing broad-scale testing of just anybody. They only were testing people that had symptoms. So they were mostly giving tests to people that they were pretty sure had the virus. So under those conditions, really what you were getting was a sample of the infected population that looked very much like Poisson. This was the people that happened to have severe enough symptoms or contact patterns that were known such that you actually observed them. But they were just a fraction of the total number of infected people. And so the variance that you had from that was roughly Poisson. There was an issue though, which is that if they were reporting the cumulative number of cases per day, and those measurements are not uncorrelated. The cumulative number of cases today is heavily correlated to the cumulative number of cases yesterday, and even the noise on it's correlated, because if I measured high yesterday, I'm more likely to measure low today, and vice versa. So because of those problems, we had to change the data to being new cases, which wasn't what was being reported. The new cases reported each day are a lot more likely to be uncorrelated, and you can use them for the Poisson measurement. But we are using Poisson likelihood. And then we wanted to consider two models. Now, you guys know, because we did it several times in this class, epidemics, you model them using like the SIR or the SEIR or some variation on susceptible infected recovery. But a lot of people early on in this pandemic were inappropriately applying that model to the data. The reason why it's inappropriate to apply that model at the beginning is because it will interpret changes in the infection rate as being evidence, for instance, that you're running out of susceptible people. But at the beginning of the pandemic, the concept that you're running out of susceptible people it's laughable. It's not realistic. So instead what you would do is you would assume that the number of susceptible people is essentially constant, that you're not really digging into that at all. You haven't substantially changed the number of people who are susceptible to the disease. And if the number of susceptible people is constant, the SIR model breaks down just to being exponential growth. But the question that I was interested in was, is this exponential growth with a constant growth rate, or were the interventions that they were doing having any effect which would cause the exponential growth rate to change? And so we were going to fit this then to two different possible models, one being one-phase exponential growth, and then the second one being exponential growth that at one point shifts to a slower exponential growth rate. We'll fit both of those models to the data and see which one fits better. The code for that, for the two-phase, it's got two-phase exponential growth has got 4 free parameters. The first one being the initial conditions, the number of infected people at the beginning. And then the second one being the initial exponential growth rate, A1. So if you look here, we've got this here. So first phase here is just x of 0 times e to the A1 times time. But then the second phase, it slows down to A2, which is the second growth rate. And it slows down, the transition time is at time t1. So those are our 4 parameters. And then for that second phase growth, we make it so that the final condition at time t1 is equal to the initial condition at time t2. So basically we have here just this shifted version, right? Where we have e to the a times t1 times x0. That's the final value of m1 before it switches to the second growth phase. And then here we've got the second growth rate a2, but I shifted it by t1 so that it matches with this code. And then we just put the two of them together where the total measured is comes from m1 when we're before t1, and it comes from m2 when we're after t1. So that basically just gives us exponential growth that then slows down to a slower exponential growth phase, but has the same number of infected people at the transition time. This isn't actually the best way to model this. After all this was done, I realized that what this isn't taking into account is the possibility that when we switched whatever we did at time t1 that switched the exponential growth rate may also have taken some infected people out of the system, or some susceptible people, that it might have actually changed those numbers, in which case it would have been better to model this against, instead of modeling it against the cumulative number of people that were infected, it would be better to model it against the new number of people who are infected, which also grows exponentially, but then allow another parameter that basically lets us shift the intercept at T1. Because again, if the idea was, everybody stay home, that might actually significantly reduce the number of infected people that are capable of infecting other people in a way that's not just modeled by a reduction in the growth rate. But as you'll see, this model, even though it had some assumptions that are a little bit shaky, namely the idea that after this transition point, we still have the same number of infected people potentially infecting other people. It still fit the data extremely well, so that assumption might have been valid anyway. But that's the idea. That's the two models. And then for me to get model 1, all I have to do is make T1 larger than the last day and make A2, it doesn't matter what A2 is, but you can just make it 0 because that's a special case. So model 1 is a special case of model 2. Just make the transition time after the window that we're modeling. So then for the likelihood code, again, the inputs to it, theta, the guess that we have for those 4 parameters. Oh,
sorry.
Okay. The days is just the time points that we have data from, and then new data is the data of the number of infected, the number of new infected people at each of the time points from the previous one. And then you have here predicted data. We use that previous code with our guess at theta to, and then these two things are going in there, but they're not actually being used by the prediction. They're just going in there so that I have the same inputs to all of the equations. But just uses theta and then generates a set of predicted data at the same time points as the new data, so it can compare the two. And then it does the likelihood function by taking the Poisson PDF, centered at the predicted data, and evaluated how likely is it that we got those new data, the actual measured number of new patients at each point. And then the rest of this code you recognize, the minus 800, just in case we have a minus infinity somewhere. Summing it up. So here's the optimal fit for the two different models. Red dashes is the two-phase model, and blue dashes is the one-phase model. By running an optimization, and I think for this one I actually used fmincon, it worked. We got a maximum likelihood for model 1, that's the one phase. The maximum likelihood was minus 1,797. And for model 2, the maximum likelihood was minus 1,481, which is substantially larger than minus 1,797 797, right? So this one, this is clearly a better fit. But you can also just see from this plot that it's a
Are
better
the green
fit.
X's the true data?
The X's are the, yeah, those are the measured data.
Okay.
And then the dashed lines are the predictions by the two models. So with these two optimal fits, oh, and this is on a log scale too, because it's easier to see how good the fit is on a log scale because exponential functions become straight lines. It still works on the regular scale, but it's just not as easy to visually see what's going on. So this first model had two parameters, and so the calculation for AIC is going to be 2 times 2, so 4, minus 2 times the log likelihood. That comes out to an AIC of 3,600. Model 2 had 4 free parameters, so AIC becomes 8 minus 2 times this, 2,970. Remember, for AIC model selection, the one with the smaller AIC wins. That's the better model. So this one is better. And in terms of how much better, we can talk about the delta AIC between these two. That works out to 630, or minus 630. So if you were to do a residual likelihood, saying if both these models are possible, what's the residual probability that it's actually the one phase instead of the two phase, just by randomness in your data? And the answer to that is, that would be e to the minus 315. E to the minus 315, of course, is like 27 zeros. So this is the right model. This model is crap. So then we basically say, okay, we did have we had two-phase growth. Something happened that changed the growth. And it seems to actually fit pretty well, right? We're not looking at the, even at the beginning here, where these numbers are falling below the curve. That's actually easily explained by the fact that right after this thing emerged, we were hardly doing any testing. So all of those numbers, it's not surprising that they were falling below the predictions. So this is a pretty good fit. Now the question is what can we say about when the change happened and what do we know about the growth rates? So to do that, we have optimal guesses, but we want to know something about the range. So to do that, we run MCMC. So here's the MCMC code. It's a few pages long. So I did this for 4 million iterations, so n equals 4 million. For the theta init, this was the maximum likelihood values for the 4 parameters, so plug those in as our initial guesses. Incidentally, that's saying that the best fit said that there were 32 infected people at day 0 as being its best guess. And that the initial growth rate is 0.16 per day, and it drops to 0.06 per day at the end. And it switched at day 23.3. Now, MCMC code, right, you initialize your likelihood by checking out what's the likelihood of that first guess, using the same likelihood function I did for the optimization. Make some blank spaces to hold your parameters and likelihood values. Then fill in the first line of those using the initialization values. And then for I equals 2 to n, do your Gibbs sampling. So in this case, I did do Gibbs sampling. There were 4 different parameters. I grabbed a random number between 0 and 3, and based off of that, oh actually, no, this is a mod one. I did what I told you guys not to do, which is here, basically, I just marched through the parameters. So mod is modulus, and basically if mod I 4 equals 0, that means that I is a multiple of 4. And so if that comes up, it's going to be 0. Every 4th one, it'll choose this one and change the first value of theta. I used a log normal prior. 3.5 is the log of the initial guess. 0.15 is a nice wide range that turned out to be, I played with that till I got it wide enough so that it was non-informative. Same story for the prior distribution for the other 4 parameters, except for the parameter for the switch time. For that one, I did a uniform distribution because the posterior distributions didn't look normal, and so I figured it was safer to use a broad uniform distribution between day 19 and day 24. And then I was able to show that was non-informative because the posterior distribution didn't get anywhere close to 19 or 24. So that meant that saying that it was between 19 and 24 was good enough for me then to say on the output that it turns out that it's between day 23 and 23. That was broad enough not to influence the results. But yeah, this mod basically says whenever it's divisible by 4, do this one. Whenever you have a remainder of 1, do this one. When you have a remainder of 2, do this one. When you have a remainder of 3, do this one. I do not recommend doing that. The way that I showed in class of doing the switches is better because technically for give sampling, you're supposed to randomize which parameter you pick next. This doesn't randomize. This just goes 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. But that works so long as the parameters aren't too heavily correlated in other problems. So you can get away with this, just don't do it because it's wrong. Then after you pick your new random parameter, you assemble it, you do a likelihood test on that guess for the parameter, and then you basically do the Hastings algorithm. If it is better than the previous value, or if it's worse but the difference is smaller than this random number between 0 and 1, then you store it. Otherwise, you restore the previous value. Basically repeat it in the chain and keep going. Do this 4 million times. And if you use the MATLAB function plot matrix, it gives you these posterior distributions. So you remember I told you that shotgun blasts look great. So we've got shotgun blasts for all of our pairing-wise except for these two. But that's not surprising. When you do linear regression, the slope and intercept are always inversely correlated like that, and this is the intercept and this is the slope for the first phase. But the rest of the parameters are nicely uncorrelated, and we're able to compute confidence intervals from looking at these distributions. So those are our 95% confidence intervals, and we can figure out when did it switch. These are the ones we really care about. So this is when did it switch. And these two are how fast was it growing before and after the switch. So here was some of the cool things that came out of this. First of all, definitely two-phase growth was justified. The first growth rate phase was between 0.15 and 0.17 per day. The second growth phase was between 0.06 and 0.07 per day. So these were really tightly distributed. We had actually good data here to narrow in on these growth rates. The transition date was April 6th. And the uncertainty in that, the 95% confidence interval, was 6 hours wide. So it was April 6th. That was the day that the transition happened. Whatever happened on that day dropped the infection rate by about 2.5-fold. And so the question was, what did happen on that day? Well, nothing happened on April 6th, but there's an incubation period for the virus. It's about a week long, and if you look a week prior to April 6th, that was the day that Delaware closed all the public schools. So that day, which also forced a bunch of adults to stay home with their kids, that's what changed the exponential growth rate, that intervention. So I thought it was pretty cool. All the data methods that we were using pretty much let us see in real time what was happening here. But of course, there were a bunch of epidemiologists that were out ahead of me on this one. So I stuck with HIV, but still. That's the methods that we're using. And that's how they could be used here.
How do we not be in the lead of the
Sorry?
I was just saying that it's so cool that like if you can actually see it, that'd be a difference.
Yeah, I was really surprised by this 6 hour, 90, like I'm not used to things coming in that tight. It really was like, what day was it? April 6th. What's your boundary? Well, early in the morning, April 6th, until early afternoon, April 6th. That's pretty much what had happened. It was amazingly tight. Considering that the data points themselves were only being sampled once a day. Usually you have uncertainties span at least a few of your data points here, but it was literally going at this rate and then a sudden shift to a new rate that was really tight, so. Yeah,
If you add vaccinations, in addition to this model, could you add like a third exponential?
oh, sure, and actually we did that, just people in my lab were doing this for fun as the thing went on, and you could see a couple other transitions. The other transitions that happened throughout the pandemic were less dramatic. But we had actually had an idea about going through all the data and trying, because Delaware did a lot of things on that day, right? Recommended people stay at home except for essential workers, shut all the schools, mask wearing didn't start yet at this point. But we thought it would have been interesting to do this for lots of different municipal areas that were reasonably isolated and see if we could then disaggregate the effects. So this particular municipal area did these 3 interventions on this date. This other one did these 3 interventions that aren't perfectly overlapping with these 3. We get effect sizes for all of the combinations of interventions, and then can we back out the estimates for how much of a difference each intervention made. It was a good idea, but it was sort of I figured somebody else would do it. As far as I could tell, they didn't. And it also probably would have been really, really noisy. But I liked the idea because it might have been able to make us see, like, what is it that's helping the most? Masks, are they important? I mean, the answer for that, they did some studies showing that they were. But we had a whole bunch of other things that we were doing that had various societal costs associated with it. Closing schools. Seems like that made a big difference here, but then there were a bunch of arguments later on that closing schools wasn't that important because kids weren't transmitting it, which I was always skeptical of because I was looking at this data as well, if kids weren't transmitting it, why did it make such a huge difference when we closed the schools? So it was, zeroing in on that I think would have been useful. We could say things like, oh, we're letting indoor dining happening, that's really dangerous, or oh, we closed all of these businesses, which has a big cost, but turns out to make very little effect on the infection rate. It would have been nice to know that, but it's all kind of a moot point now, I think. So, but yes, you could basically see how the vaccines are changing things. The biggest thing, though, with vaccines, I think that it's not exponential growth anymore. Most places that have the vaccines, the spread has dropped below exponential and more into sort of like residual spread. Like in California, you can see that their number of new infections is just plummeting. They managed to get over that threshold. I imagine we'll be soon in a similar situation. Anyway, that was last year's class. It happened to hit right at the right time. We had that example.